Hello ladies and gentlemen, I'm honored to have the chance to address on this special occasion. The topic of my paper is Hippie, a data parallel pipeline approach to improve memory efficiency and scalability for large data training. The outline of my talk is as follows. First, I will introduce the background and motivation. In recent years, the scale of deep neural network models has grown rapidly, and there are more and more super large models. Therefore, two main challenges come to large data training: memory limitation and low scalability. Most of the existing parallel approaches focus only on improving throughput, but we hope to get higher scalability and lower memory usage, which makes more sense for large-scale data training. To better measure the efficiency of parallel training, we define a new index called memory efficiency, ME. The ratio of the average throughput per device to the maximum memory consumption per device is defined as memory efficiency. Our goal is to get as high ME as possible. Next, we will introduce our parallel training approach. We propose Hippie, a hybrid parallel training framework that integrates PMP and DP. Figure shows a high-level workflow of Hippie, which mainly consists of planner and the runtime schedule. The runtime schedule includes communication schedule and the last stage schedule. Let's explain how communication schedule works first. The key to improving throughput and scalability is to reduce the proportion of communication time and idle time as much as possible. We can see that there are many idle bubbles existing in synchronous pipeline. We introduce communication schedule to use the idle time, differed from the orders and communications after computations in the usual DP. Hippie advances the communication operations and covers it within the process of computations. Since the gradient communication in the formal part of the pipeline is advanced, we created a buffer to store the gradient. We will demonstrate the training process in Hippie's one step. After several forward computations, as shown in the figure, stage 0 will first get the gradients from the buffer and then perform the or reduce. Similar to stage 0, stage 1 will get the gradients from the buffer first as well. At this point, all the forward computations have been completed, and Hippie starts to perform backward computations. The or reduce will average the gradients between workers and store it for the update later. The same to stage 0. The communication and the update order of stage 2 and stage 3 has not changed, and they do not need to computate with the gradient buffer. For stage 0 and stage 1, after the backward computations, the stage needs to perform two operations. First, store the newly calculated gradient into the buffer, and then get the averaged gradients for the update. After the update, Hippie was ready for the next step. These are the details of the training process for a single step in Hippie after communication schedule. Later experiments showed that it significantly improved the scalability of training. The following is the last stage schedule. After several forward computations, the intermediate results and the boundary data of graphs need to be stored in the memory, which significantly increases the memory consumption. The last stage with large output may become the memory bottleneck. Therefore, we introduce the last stage schedule to reduce the big peak memory consumption in the last stage. Hippie will schedule one forward of mini-batch followed by one backward strictly, advancing the release of the graph. Figure shows the specific workflow of the last stage, and the schedule above will not affect the other stages. Then, pipeline planner is responsible for generating an efficient pipeline. Most of the existing parallel approaches only consider throughput. In contrast, Hippie's optimization goal is memory efficiency, which contains both throughput and memory footprint. A pipeline planner will not only partition the model to balance every stage, but also need to select specific layers to apply recomputation. The recomputation operation will reduce the memory overhead. Due to time constraints, the specific formula will not be explained in detail here, which can be referred to in the paper. Next comes the evaluation section. We evaluated the performance of Hippie among 4 device DNA models, including image classification and NLP tasks, which is shown in table. Altogether, 4 approaches are involved in our experiment. Hippie. Then the method combines GPIP and DP. And the method combines MP and DP. We will compile the throughput, memory, and memory efficiency of this method. Figure shows performance for all models in fixed number of GPU equaled 16. With the contribution of the communication schedule, Hippie maintains a decent throughput. Meanwhile, as shown in the fourth column, Hippie could keep the memory footprint into a low value, only half of DP in some cases. The memory efficiency is significantly improved, which is always the highest among the above 4 methods. As shown in the last column, Hippie could get up to 2.65 times memory efficiency in GMT8 and 4.18 times in GMT16 compared to DP. The GPIP plus DP has the lowest performance. The model size of VGG is slightly smaller than GMT16. In training VGG, most communication operations could be covered through DP overlap, resulting in high throughput, but DP consumes more memory. Finally, Hippie achieves up to 1.38 times memory efficiency compared to DP. Limited by the device memory, DP is not available in EmbeddNet. We have to divide EmbeddNet into several parts and then combine GPIP or MP with DP for training. As the figure shows, Hippie performs significantly better than the other 2 approaches. Surprisingly, Hippie outperforms GPIP plus DP with up to 3.46 times memory efficiency. It can be seen that Hippie has more outstanding training efficiency for large-scale models, especially those cannot be trained by a single GPU. Hippie also maintains high scalability. In this section, we carry out the comparison of scalability with fixed batch size per GPU. The scalability of Hippie has significantly improved thanks to hidden communication. The GMT, which has the highest proportion of communication overhead, is selected for the experiment. We use the throughput of 4 GPUs as the benchmark. Then, the throughput of 16 GPUs in linear scaling should be 4 times. The figure shows the throughput of both approaches and compare it to ideal linear scaling results. As shown in the figure, Hippie can maintain a scaling efficiency of over 90%. In contrast, DP can only keep 60 to 70% scaling efficiency. The figure shows the convergence of Hippie. From our observation, Hippie can reach target occurrence in a closing number of epochs to DP, and the increase in throughput is equivalent to the increase in training speed. The last part, conclusion. First, we present a distributed training framework which integrates pipeline model parallelism with data parallelism. Then we introduce the communication schedule, the last stage schedule, and the pipeline planner. These optimizations have achieved excellent results. Finally, Hippie outperforms DP by up to 4.18 times memory efficiency. That's all for me. Thank you for listening. Any questions are welcome to communicate with me.